So in this topic we will discuss the analogy, right? The analogy of rod as a spring, right? The rod can be treated as the spring, right? For example, suppose this is the rod, right? At the rod of the length L, the mass M, its young modulus is Y. So this rod can be treated as a spring. For example, if the young modulus is Y, the length is L. All right. When you apply the force, what will happen? There will be some elongation in the spring, right? There will be some elongation in the spring, and this when you apply some force. All right. So if the young modulus is Y, so stress upon strain, if you consider the area of cross section is to be A, right? So stress upon strain is the young modulus. What is the strain? Delta L upon L. Is it clear or not? So it may be written as F upon A delta L into L, right? So F is equal to YA upon, this is capital L, right, N into delta L. Is it clear or not? So listen one thing, if you assume this delta L to be X, if there is the elongation, right, in this rod by applying the force, right, is X. So now you can think, if there is a spring, right, and the spring constant is K, if you apply the force, there is the elongation in this spring, right? What is the elongation in spring? F. So F is equal to what? Say K into X, right? So force is also proportional to the elongation in the rod. Here the force is also proportional to the elongation in the spring. So if you compare both this equation, so the K of the spring constant may be equal to the YA into L, right? So the spring, this is called the equivalent spring constant. This is called the equivalent spring constant. Is it clear or not? Right? Copy this. So for this rod, the equivalent spring constant is YA upon L. Is it clear or not? For example, if there are two rods, this is the one rod, the another rod is attached end to end in this way. All right, its length is L1, its length is L2, the area of cross section is A1, the young modulus is Y1, its area of cross section is A2, the young modulus is Y2. Is it clear or not? Right. So you may consider that there are two springs, right, are connected in series. Its spring constant is K1 and its ring constant is K2. What is the value of K1? K1 value is nothing but Y1 A1 upon L1. The value of K2 is nothing but Y2 A2 upon L2. All right. This is Y2 A2 upon L2. So what is the equivalent spring constant util? If you consider, right, the equivalent spring constant when the spring are in series, so how to find the K equivalent? Please tell. 1 upon K1 plus 1 upon K2. All right. So what you have to find? So equivalent, for example, if this is the rod, and if you want to find the rod, the equivalent, the K equivalent for this rod. So the K equivalent for this rod would we find with the help of this. For example, what is the 1 upon K1? Say Y1 A1 upon L1 plus Y2 A2 upon L2, right? This is the K equivalent, right? And the K equivalent is L1 upon y1a1 plus L2 upon y2a2. In this way, you can find the K equivalent. Is it clear or not? You tell. Right, special case, special case. What is the special case? If the area A1 and A2 are equal, are you getting or not? So what will happen then? 1 upon K equivalent is equal to 1 upon A, L1 upon Y1 plus L2 upon Y2. This is the K equivalent, right? And for this K equivalent, the length is what? For this equivalent rod, the length become L1 plus L2, the area become A, and its young modulus become Y, or you can say Y equivalent. So for this rod, the K equivalent is what? Y equivalent into area, Y equivalent into area divided by L1 plus L2. Are you getting or not? Although the K equivalent for any two rods, the length L1 and L2 are different, area A1 and A2 are different, young modulus materials are different. So K equivalent will be found with the help of this expression. But sometime if the areas are same, all right, so the K equivalent is what? It is equal to 1 upon Y equivalent A upon L1 plus L2. So this area will cancel out. L1 plus L2 upon Y equivalent, it means the young modulus equivalent is equal to L1 upon Y1 plus L2 upon Y2. Is it clear or not? Now you may simplify further and you will get what? The young modulus equivalent is equal to L1 upon L2 divided by L1 upon Y1 plus L2 upon Y2. Is it clear or not, you tell? This is the equivalent young modulus of the two rods connected. If these are the two rods, the L1 and L2 are the length, all right, they are connected in series like this. The young modulus is Y1 and Y2. So what is the equivalent young modulus given by this formula? Also the special case, if, right, it is L1 L2 Y L2 Y2, if L1 and L2 are equal, right, then what is the young modulus? Equivalent young modulus is L plus L upon Y1, L upon Y2. So it is equal to 2L, and Y1 Y2, when you will simplify, take L common, it is Y1 plus Y2 you will get. This L will cancel out. So it is 2Y1 Y2 upon Y1 plus Y2. This is the equivalent young modulus of the two rods when the two rods of the same length, right, and the same cross section, right. This is the equivalent young modulus if the two rods of the same cross section and the same area, Y1 and Y2, the length is L, the length is L. If they are connected in series, so their equivalent young modulus of this rod will be equal to what? 2Y1 Y2 upon Y1 plus Y2. Listen one thing, if the length L1 and L2 are different, but their areas are same, so the equivalent young modulus is given by this formula. The rod you may make, this is the rod of the length L1 plus L2, the area is A, and what is the equivalent young modulus given by this? So if you write it in simplest way, L1 L2, right, if you take the LCM, Y1 Y2 upon L1 Y2 plus L2 Y1. This is the equivalent young modulus if L1 and L2 different length having the different young modulus are connected in series. So their equivalent rod whose length is L1 plus L2 and the equivalent young modulus is given by this. In this case, If L1 and L2 you put equal, right, then the young modulus is 2y1 y2 upon y1 plus y2. You have to remember, if both are different, then the young modulus, right, cannot be found, right? Only the k equivalent can be found for that. Are you getting or not? Copy this. Now if you consider the rods are in parallel, right, rods are in parallel. If rods are in parallel like this, suppose these are the two rods, right, like this, they are connected in this way. The length is, you may assume the length are same, right? You may assume the areas are different. Assume areas are different. So they are connected. The young modulus is y1, young modulus is y2. Are you getting or not? Right. So this can be replaced by the two spring in parallel. All right. So this is the K1 and K2. So what is their K equivalent? If they are connected in parallel, so the K equivalent is nothing but K1 plus K2. And what is the K1? K1 is L upon Ka. Right. What is the equivalent? What is the K1? Say L upon L upon y1 a1. And what is the K2? L upon y2 a2. And this is the K equivalent. Is it clear or not? Yes. What is the value of the K? What is the value of the K? It is L upon y or not? Tell me. L upon ya? Is it correct or not? You tell. L upon y, sorry, K is nothing but A1 y1 upon L. K2 is equal to what? It's spring constant A2, right? This is equal to A2 y2 upon L. Is it clear or not? You tell. If L1 and L2 are different, you may write this. L1 and L2 are different. Is it clear or not? You tell. So if you consider the rod, the equivalent rod, if you consider, the length is same, right? And the area become A1 plus A2. And the young modulus is y equivalent. So what is K equivalent? You tell. K equivalent is A1 A into y equivalent divided by L. Is it clear or not? You tell. So if K equivalent is K1 plus K2, where K1 and K2 are this, if length are equal, so the K equivalent will be found. What is the K equivalent? You will write the K1 plus K2. What is the K1 value? You tell. It is A1 y1 upon L plus A2 y2 upon L. Right. It is A1 plus A2 y equivalent upon L. L will cancel out. Is it clear or not? So yeah, what is the young modulus? Equivalent young modulus is A1 y1 A2 y2 upon A1 plus A2. Is it clear? Please tell. This is the equivalent young modulus. Special case. If areas are equal, that is both rod having the same area A, the young modulus is y1, the another rod is connected in parallel, it is area A, it is also area A. So if you consider the area to be 2A, what is the equivalent coefficient, equivalent young modulus? Is equal to ay1 ay2 divided by 2A. The equivalent young modulus is y1 plus y2 upon 2. Right. So this is the equivalent Young modulus of the two rods connected in parallel. Their length are same and the areas are same. And the previously we have found if these two rods having the same length, having the same cross section area, but y1 and y2 are connected in series, so the length become 12, the area become A, and the equivalent Young modulus is 2y1 y2 upon y1 plus y2. We had derived before this. So at least two cases you have to remember in parallel and in series for the equivalent Young modulus. All right, copy this. So let's see one example related to this. Right, if this is the rod, right, the rod is of length L, the mass M, the Young modulus is Y, the area is A, right. If a mass small m is attached to this, right, and it is stretched a little bit and it is released, when it will oscillate, so therefore it will oscillate like a spring, although it is a rod, right. You may consider the mass m is hanging from the one end, so this rod is very much similar to the spring, right. So if this mass is little bit elongated, right, it is displaced and released, so it will oscillate about its mean position like it was connected with spring. So what is the time period for this oscillation? Time period, therefore, for small displacement, for small displacement, time period of oscillation, time period of oscillation. What is the time period of oscillation? Is equal to 2 pi root m upon k. What is k? K is the equivalent spring constant, and what is it? Ya upon L. Is it Ya upon L or not, you tell? Yes, so therefore, what is the time period of oscillation for this mass? 2 pi root small m. M is the mass, and what is its equivalent spring constant? Say Ya upon L. So time period is 2 pi root ml into y into a. Is it clear or not? Right. In the same way, suppose there are two rods, right, connected end to end like this. Suppose the areas are same, right, and length is different, L1, L2. Are you getting? And another mass m is attached to one end, right. So again, for small displacement, you have to write the time period of oscillation, right. So this is equal to what? Say this is equal to or equivalent to the two springs constant K1 and K2 are connected in series and the mass m is hanging. When it is displaced little bit, it will oscillate about its mean position, and the time period is given by t is equal to 2 pi root m upon k equivalent. And what is the k equivalent? Please tell. In the series, the k equivalent is k1 k2 upon k1 plus k2. Is it clear or not? What is k1? Young modulus is y1, Young modulus is y2. So the k1 is a y1 upon y1 up y1 a upon L1. K2 is what? Y2 a upon L2. Y1 a upon L1, Y2 L2 upon L2, right. Young modulus is stress upon strain, right. Ya upon L, yes, Ya upon L. Are you getting or not? So what is the k equivalent value? I will write from here, y1 upon L1 a into y2 L2 a divided by y1 L1 a plus y2 L2 into a. Is it clear? So we have to put the k equivalent value over here. So 1 a will cancel out, in y1 y2 upon in the numerator 1 y1 y2 upon L1 L2 into A. This is y1 upon L1 plus y2 upon L2. If you further simplify, this is y1 L2 plus y2 L1 and y1 y2 into A, because if you take the LCM, the L1 L2 will multiply and they will cancel. So this is the K equivalent. So what the time period expression you will write for this? T is equal to 2 pi root m upon K equivalent is y1 y2 A, all right, divided by y1 L2 plus y2 L1 is equal to 2 pi root m y1 L2 plus y2 L1 divided by y1 y2 into A. Is it clear or not, you tell? Right. What may be given? They may give the different length. Either L1 and L2 may be the equal, or they may give it is L or it is L by 3. In the same way, you can write the expression for the time period of oscillation for different combination for the rod. Whether it is single rod, whether they are connected in series, whether they are connected in parallel. So they will ask you find the time period of oscillation. If it is displaced, a small displacement is given to this block. Are you getting or not, Parsha? Please copy this. So read this question. In this question, a mass M is attached with the rod, right? Combination of the rods. Suppose this is the rod, the length is L1, A1, Young modulus is Y1. The another small rod is over there. The length is L2. The mass is hanging like this. Its area is A2. The Young modulus is Y2. So for a small oscillation, you have to find the time period, right? So it can be replaced by the two spring connected in series or not, you tell? K1, K2, and this is the mass M, right? So the time period will be equal to T is equal to 2 pi root M upon K equivalent. And the K equivalent, we have to find the K equivalent. What is the K equivalent? K1, K2 upon K1 plus K2. What is the value of K1? K1 is Y1 A1 upon L1. K2 is Y2 A2 upon L2, right? The length is L2. So here the K equivalent is Y1 A1 upon L1, Y2 A2 upon L2, right, divided by Y1 A1 L1 plus Y2 A2 upon L2. Is it clear or not, you tell? So this is the K equivalent. So if you put the K equivalent value over here, you can get the answer. Wait for 1 minute. It may be written as Y1 Y2 A1 A2, Y1 Y2 A1 A2. If you take the LCM, the Y1 A1 multiply by L2, Y2 A2 multiply by L1, and L1 L2 will cancel out. So this is the K equivalent. So the K equivalent may be written as Y1 Y2 A1 A2 divided by, right, all this thing. So it comes in numerator. So it is Y1 A1 L2 plus Y2 A2 L1. So this is the time period of oscillation. Are you getting or not? This is the time period of oscillation. Copy this. So read this question. In this question, there are a ball hanger is massless, right? A ball of mass M drops from a height h. Suppose these are the two rods, right? And this is the hanger. And the ball is dropped, mass M, the U is equal to 0, right? And this is the height h, suppose, right? You may assume, right? It is the rod A1, Y1, and the length is L1, all right? There is another rod, length is L2, A2, Y2 is the area of cross section in Young modulus. Are you getting? Neglect overturning, find out the maximum elongation in the rod. Assume these rods having the less mass, right, or the mass less. The maximum elongation in the hanger, if this ball come with some velocity v, so it will start moving and you have to find the maximum elongation in this case. Is it clear or not, you tell? Right. To solve this question, let us consider one another example. For example, if there is a spring, the spring constant is K, there is a hanger. If the ball of mass M is released from height h, after collision with this, right, it is stick, right, it stick with this. So what is the final, what is the maximum elongation? What will happen, you tell? It will start moving when collision occurs and this stick with this. In the final elongation, right, the ball and the hanger will be stop again. Is it clear or not? So this is the x, maximum elongation in the spring, right? So the final speed is 0. Are you getting or not? So what, to find the maximum elongation in the spring, what concept you will apply, you tell? It is massless, suppose. The concept we will apply that the decrement in the potential energy, if the M was present over here, what is the decrement in the potential energy of mass M? Say mg h plus x max, right, is stored in the form of elastic potential energy of the spring. And what is that? Half k x max square. You understand this concept or not, you tell? Varsha, total potential energy mg h plus x max is stored in the form of elastic potential energy of the spring, which is equal to half k x max square. Because what is the elongation? Initial elongation is 0. The final elongation in the spring is x max square. You understand this concept or not, you tell? Right. Varsha, please tell. Right. Now similar concept we have to apply. These are the two rods. So these rods are maybe replaced by, these two rods may be replaced by the spring, equivalent spring constant, right? And what is the equivalent spring constant? Tell me. This is the equivalent spring constant, equivalent. Is it clear or not? And again, the mass M is released from height h. When this is the hanger is the massless, no loss of energy, it stick with this. And what is the elongation? The maximum elongation is supposed to be x max. So this is the mass M, the potential energy. What is the height? H plus x max. So what you have to do? The same concept. Again, what you have to apply? The mg h plus x max is equal to half into k equivalent into x max square. Now what is the k equivalent? Yes, please tell. The k equivalent is nothing but k1 k2 upon k1 plus k2. And where, what is k1 and what is k2? k1 is y1 a1 upon l1. k2 is what? y2 a2 upon l2. You understand this thing or not? Please tell. Yes. Now this x maximum, this is the equation, the quadratic equation in x max. So we can find this, multiply by 2mgh plus 2mg into x max, fine, is equal to k equivalent into x max square. So simplify this, k equivalent x max square, right, minus 2mg x max minus 2mgh. So this is the quadratic equation. Are you getting or not? From this quadratic equation, we know the value of the k equivalent from these two expressions, right? H is known. So how to find the x max? So the x max may be written as minus b plus minus root b square minus 4ac upon 2a using the Dharacharya niyam, right? So x max is equal to what? Minus b. What is minus b? Minus 2mg plus minus root b square minus 2mg whole square minus 4 into a into c minus 2mgh. fine, upon 2 into a k equivalent. So if you write the x max over here, minus minus become plus 2mg divided by 2k. I'm writing separately. This is plus minus root over 4 mg का whole square minus plus 8 k equivalent into mgh divided by 2 into k equivalent. 2 will cancel out, mg upon k equivalent, plus to find the maximum elongation you have to take the plus, right? Because otherwise it will be negative. So only take the one root which is positive, and when the 4 comes out, the 2 will cancel out. In the square root, this is mg whole square plus 2k equivalent mgh. So this is the maximum elongation in this system, in this hanger. When the ball is dropped, it hits and the system start moving and stop again at this point. I think it should clear. Is it clear or not? You tell, please tell. Varsha, copy this. So read this question. In this question, a composite heavy rod made of two materials, right? And the length is LU. This is the upper rod and upper rope. This is the lower rope, right? Vertically suspended vertically from high ceiling. The ratio is given LU LL is equal to 1:2. AU AL is equal to 2:1. Density DU DL is equal to 2:3. What is the ratio of the maximum step in the two ropes? If you consider this is the upper, right, and this is the upper rope and this is the lower rope. So in the lower rope, this is the point where the tension, where the stress will be the maximum. So it is the T1, right? Or you may assume the TL. Maximum tension will be over here. How? Suppose this is the mass M1G, right? So what is the tension over here? The equal to what? Say M1G or not, you tell. Fine. And the tension TU, you may assume. What is the maximum tension on the second rod? It is at the highest point. It is equal to what? Say, suppose this is the M2G. So M1 plus M2G. Is it clear or not? So they are asking the ratios of the stress. So what is the maximum stress? The maximum stress in the lower rod is nothing but TL upon AL divided by maximum stress in the upper rod is equal to AU. This ratio they are asking. Is it clear or not, you tell? So TL upon AL, what is the TL? Say M1G upon AL divided by M1 plus M2 G upon AU. Right, GG will cancel out. M1 upon M1 plus M2 AU upon AL. What is M1? Is the mass. What is the mass? M1 M1 you may assume M lower, or suppose this is the M1 and this is the M2. What is M1? Volume into density of lower, right? DL. What is the volume? Say A1. Are you getting or not? What is the AL into length L into DL? Is it clear or not? And what about the M2? M2 is nothing but volume into density of the upper. What is the volume? Say area into length upper into density upper. So now we have to find this ratio. What is M1? You tell. AL, LL and AL, LL and density L divided by this plus this. Some ratio is given or not, you tell. Wait for 1 minute. Wait for 1 minute. You may write in this way. 1 plus M2 upon M1. And what is AU upon AL, it is 2:1. Are you getting or not? Now, M2 upon M1, ratio you can find. What is M2? AU, LU, DU upon AL, LL, right, and DL. So what is the AU upon AL? It is 2:1. What is LU upon LL? 1:2. What is DU upon DL? Is to 2:3. So this is 2/3. So here this is 1 upon 1 plus M2 upon M1 is 2/3 into 2 is equal to 6 upon 5. Right. So this is the correct answer. Right. 6 upon 5. That is, they're asking the reciprocal, you may cite 5/6. Right. So C option is the correct option. Right. Copy this.